Hello, in this video, we'll talk about analyzing graphs and functions. In one of my prior videos, we've studied function from an algebraic point of view. In this video, we'll be studying functions from the graphical perspective. So just as a brief introduction, the graph of a function f is the collection of ordered pairs, right? Some x comma f of x, such that x is in the domain of f. So let me just write that down and then we'll look at what that means. So once again, a graph of a function f, so we have some function f, is the collection of ordered pairs x comma f of x, such that x is in the domain of f. So what does that really mean to us? It means that if we have the xy axis, and we have some function called f of x. Okay. So let's say we have a function here. Okay. This is the function that we will call f, okay, or f of x. Now, if we have, let's put some numbers in here. If this is 1, this is 2, this is 3, and so forth. Okay. If we have an x value, let's say we pick some value here. Okay, this is x. So x is equal to 2 at the current moment. Now, if we plug that into the function, okay, then, so when x is 2, okay, f of x, if I give you f of x is going to be the function, then f of x is equal to f at 2. So you'll take the 2, you'll plug it into the function, and this will be the function f of 2, which is the y value. Okay, and that's how we get that the point here is x comma f of x. Okay, and you can do this for many, so that will just give you 1 point on the graph. That's that point on the graph, and I can do this and get many points. And that's how we used to do it, because we always used to have a table of values, right? So for every point, we have some x comma f of x. So that's what we mean, that if we have all of these points here and we plot them, we will get a graph. So for example, if I ask you to graph, example, sketch the graph of f of x equals x squared plus 1. Well, the way we do this, first we create a table with random x values. Okay, so generally what we do, we make a table. Okay, we make a table, and we said we have a table of x and y, and we choose some values, -4, -2, 0, and let's say 3. Okay, and the function we have is f of x is equal to x squared plus 1. So what is f of minus 4? Remember here that this is the x value, okay? So if we plug in minus 4, we get minus 4 squared plus 1. And this is now equal to 4 plus 1, which is equal to 5. This is my f of negative 4 value, which is the y value. And that is equal to 5. Okay, so this point here is 5. And this is the point x comma f of x, where this here, the x is negative 4 and the y value is 5. And if we continue doing this, if we continue to do this, which you can try on your own, when you find f of negative 2, okay, f of negative 2 now will be equal to minus 2 squared plus 1, and this becomes 4. Made a mistake. This should have been, let's erase that. This is 16 plus 1, and that is 17. So my f of negative 4 is equal to 17, which is the same as the y value, okay? This is your y value. So this here is 17. Now, this becomes 4 plus 1, which is equal to 5. So f of negative 2 is equal to 5, which is the same as what we used to say y is equal to 5. So then this point here will be 5. And if you continue to do this, you will see that this point here will be 1, and then this point here will be 10. And if we plot those points, that's how we end up with our graph. Okay? That's the way we end up with our graph. So we have negative 1, negative 2, negative 3, negative 4. Here we have 1, 2, 3. Here we have negative, let's see, we're going all the way up to 17. So let's call this 4, 8, 12, 16, 20. This will be negative 4. So at negative 4, the value is 17, which will be just about that point here, let's say. At negative 2, it is 5, which will be just about that point. At 0, it's 1, which will be just somewhere here. And at 3, it is 10, which will be somewhere over here. You will notice that if you plot more points, you will get sort of a parabolic shape. Okay. And this is generally how we obtain the graph of a function, right? So the function f of x, which is equal to x squared plus 1, is the collection of ordered pairs. Each one of these here, at this point here, which is 3, 10, okay? This point here, which is 0, 1. This point here, which is minus 2, 5. This point here, which is minus 4, 17. These are your ordered pairs. So minus 4, 17, okay? Minus 2, 5, 0, 1, and 3, 10. These are your ordered pair. This is the set of ordered pairs. Okay. And when you plot them, that's how come you get the graph. So that was just a quick review of how you get your graph. Now also what we want to look at is how do you find domain and range of function? How do you find the domain and range of function? So as a reminder, right, when we speak of domain, domain is the set of acceptable x values. And the range, keep in mind we say a set, right? It's a collection of numbers, and that's why we write it as an interval. The range is the set of y values or output, yeah, from the accepted values. So generally we say that the domain is the x value and the range is the y value. So if we look at this, and this is very easy to tell from graphing, okay? From an equation, it's a little bit more work, but from a graph, it's not that very difficult, okay? So if we have a function, and let's say my function here looks like this. So that's closed, and that's also closed. Okay. So in this case, the x values that we're talking about here, the x values that we have here, and we can put some numbers in here if we want, right? -1, -2, -3. Here we have 1, 2, 3, 4, 5. And here we have -1, here it's 1, and here it's 2. So these values here, these x values from here going all the way up to here, okay? That's your domain. The domain is the x values, okay? And the range would be from here, okay, going all the way down to this point here. This is what we call the range. So generally, if we have to write the domain for this function would be brackets, and we get brackets because this is a solid dot. -3, comma, and notice that there is no break, there is no part in the graph, if you trace it, that is not continuous. And that will go up to 5, and once again, a bracket. So we use a bracket when the endpoint is included. So we use bracket, square brackets, when the endpoint of the graph is included, meaning it's a solid dot. Okay. So this is called your, if you want, this is called your right end point. And here we have our left end point. Okay. We have our left end point here. Now, if we look at the range the range, notice that the range, and when we write, we always write from lower, okay? So maybe we should make a note of that. Always lower number first, okay? So the lowest y value here is -1, and the highest y value we have is 2. So your range would be from, we said, -1, included -1, and because I was a solid dot, 2. Okay. Now, if we look at another example of this, we can have many examples here from the graph. Let's look at another example. Okay. So, example, find the domain and range from the graph. Below. Okay. So now we want to find the domain and the range from the graph below. So let's look at this graph. So let's say we have actually, I want to draw that on the line. Let's say we have here one. Well, let me draw my graph first. So we have a solid dot here, and then that goes up there, comes down all the way over here, and let's say we stop here. So this is X, this is Y. Let's put in some numbers now. 1, 2. Actually, I wanted to pass through a point so we don't have to guess. So here is 3, here is 4. This is -1. Here we have -2. Here we have 1, 2. This is -1. This is -2. So let's look at the domain first. The domain. Now remember, domain is X values. So on this graph, this X value here will be the first X value. So this graph is going from here all the way to this point here, right? So from here to here. Okay, that's the X value. So the domain here, now we have to be careful. Notice that this point here is a solid dot. So that means we have from, okay, from -2, comma, all the way up to 4. But if you notice, this is an open circle. So we have 4 and we use parentheses. So when the point is not included, when we don't know what it is, we use parentheses. And note, when we write domain, when we write domain on range, okay, the values is written from smallest to largest. Okay. And now if we look at the range now, look at a range, So our range is from this point here to this point here. Okay, so this is the range. This is the domain. Okay, so it's the highest y value. The graph is all the way to there, and the lowest y value. Okay, so if I write that, okay, that will be bracket, oops, will be bracket from -2 to 2. Now, if you're wondering why am I using brackets and why am I using parentheses here? So if you happen to plug, if you take this x value here, okay, if you take that value and you plug it into the function f of x or g of x, whatever we want to call this function, let's say g of x, okay? So if you take that point and you plug it into g of x, you will get -2, okay? And if you take this x value here, this x value, and you plug it into the function, you will get you will get, I'm sorry, if you take this x value here, where x is 0, and you plug it into the function, you will get +2, okay? So once you get a number, that number is associated with a closed bracket. And there are cases where we wouldn't know, okay? Let's look at one more example. Let's look at another example. So example, find the domain and range from the graph below. And here I'm giving you this graph. Okay. And the graph I'm presenting to you is this graph here. Let's call this graph h of x. So you will notice that there is no break in this function here. So the x value, the domain will be from here, and notice that it goes continuous, okay? This here has an arrow to it, so that means it doesn't stop. So this is your domain. But notice now the range would be from this point here, and notice it goes on and on, so because there's an arrow here, so it doesn't stop either, okay? So we get continuous here, and this is continuous there. So when we write the domain, the domain will be from 0, which is the x value, going all the way up to infinity. And it goes to infinity, right? It goes to infinity because we don't know where the graph stops. That graph is continuous. There's an arrow there. And infinity always gets a parenthesis. Okay. On the other hand, the range, once again, if you take 0 and you plug it into that function, well, that's a solid dot anyway. You will get 0. And also, as this graph goes out this way, it's also traveling up. So this is also infinity. Okay, this is also infinity. So in a later video, I'm going to show you a bunch of graphs, at least 6, 7 graphs that you should, which we call sort of the parent function, and you should know what the domain and range is. Okay, so this is just an example of how to find the domain and range using graphs. Okay. Now, how do we know, okay, if a graph represents a function? Okay, because not all graphs are functions. In one of my videos, I showed you that to be a function, for every input, you should only have one output. Okay. So let's look at that now. Okay. So we'll now look at the vertical line test. Okay. So the vertical line test is a tool, is a little tool that we can use to identify if the graph represents a function. So as I said before, not all graphs represent functions. And we can use, okay, we can use the vertical line test to identify if the graph represents a function. Okay. So here, for example, let's look at this graph here. Let's look at a linear graph. Here is x, here is y, and let's say I have the linear graph that looks this way. So linear y equal mx plus b. Okay. Now, you will notice that what is the vertical line test? The vertical line test is a vertical line that we draw on the graph anywhere. Okay. It's a line that we draw on the graph. And if that line that you draw touches or crosses the graph once, okay, so if the vertical line touches or crosses the graph only once, then the graph represents a function. So please note, you have to draw more than one line, right? If I continue to draw lines here, if I continue to draw lines, each one of these lines only cross once. So you want to draw a bunch of lines to see, because maybe one of them will cross, but the other one wouldn't cross, okay? So this is a function. So let's redraw it, okay? Let's redraw it. So after redrawing all my graph, you will notice that any one of my vertical lines only hit it once. So the vertical line only crosses the graph once. One line at a time, okay? One line at a time. Now, something else you will notice that note that the graph of any linear function or any linear graph any linear graph so any linear graph in the form y equal mx plus b will represent a function. So this is just something you will see as you draw, right? If we look at other examples, okay, so let's look at another example. Let's look at the graph that looks like this. So this is some function g of x. Here we have the x-axis and the y-axis. And if we draw a bunch of vertical lines, okay, you will notice that this here also is a function. This is a function. Okay. Since each vertical line only touches the graph once. Okay, once is the keyword here. If you look at another example, where this is the x-axis, that's the y-axis. Now, if I draw my first line only hit it once. But if I draw another line, touches twice. So touch, and here, touch. So this does not represent a function. There are many examples of graphs out there that will not represent a function. Yeah, many different examples of there. So you can keep doing this, right, and see that it's not. So we can do a few more, right? We can try some more. So examples, identify okay, if the graphs below represents a function. Okay. And notice we will do this by performing the vertical line test. Okay. So the first one we'll look back is one that we did above. It's the parabola. Okay. So we have the parabola. If we have our graph, we see that if we draw vertical lines on the graph, then this is a function, right? Only hit once. So yes, this is a function. You will notice that if we draw the absolute value, okay, if we draw the absolute value, and we draw vertical lines, you will notice that this is a function, right? Once, 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 once. So yes, this is a function. Yeah. You will notice that if I draw a circle and I draw vertical lines, right at this point here, it only touched once. But anywhere else, okay, anywhere else, it touches twice. So this, so no, this is not a function. Yeah, this is not a function. So we can keep doing this, right? Doing this, and you just draw and see which ones are function or not. So as I said before, right? As I said before, if we draw linear graphs, if we look at linear, and I give you, there's only 3 types of linear, or 3 ways to draw a linear graph, right? The first one is when it's in y equal mxb. Yeah. The second scenario would be a horizontal line and here we have y equals c, where this point here is c, okay? And then we have the vertical line, if we have a vertical line. And remember the equation for a vertical line, if this point is c, is x equals c. So you will notice that if we draw, right, if we draw vertical lines on the graph, this graph here, okay, this graph, it will pass the test. Yeah, it will pass the test. Likewise, if we do it for this one here, okay, it will also pass the test. But notice that if we draw it, this graph here will not pass the test. The reason we say that is because if we draw a vertical line here, it doesn't hit at all, right? and the saying say it has to hit at least once. If you draw a line right there, notice that this one hits everywhere. It's touching each place every single time. Okay, your vertical line, so you notice that the vertical line drawn will touch the graph continuously. Okay, continuously. So not just one place or anything like it will touch it continuously everywhere. Okay, so note, okay, that all linear graphs or functions except the vertical line. So I don't want to say function here, all linear graph or equation except the vertical line are functions. So only if it's a vertical line, you will notice. Now, the same thing we can say for quadratics, right? You will notice also, so note all quadratics are functions. All quadratics are functions. It doesn't matter. And when we speak of quadratic, anything that's in the form f of x equals ax squared plus bx plus c, where a cannot be equal to 0, right? Example of this is if we have f of x is equal to x squared plus 1. We saw before, I drew this before, okay? X squared plus 1 is the quadratic that looks like this. Okay, this is f of x. And you will see that if you draw vertical lines, that it is a function. Okay, this is a function. Yeah, all quadratics are functions. So in addition to this, okay, in addition now, if we move on, functions are different ways, right? A function. Or if you don't want to say write, we can say express. So one way, it can be given in form of an equation. Yeah. Or two, it could be given in the form of a table. Or three, it could be given in the form of a graph. Yeah. These are the three that we will look at. So if you have an equation, okay, an equation just means we have, for example, y equals 3x plus 4. From a table, it just means that we have a table of values, x and y. So if we have -2, this is 4, -1, we have 1, 0, 0, 2, we have 4. And from a graph, yeah, we have some form of a picture. This is g of x. So here is my graph. So how do we know we should be able to identify, I showed you the graph, right? I showed you the graph. So when we have the graph, to identify if a graph represents a function, we use the vertical line test. Okay. Always, once you have the graph, only when we have the graph, we use the vertical line test. Now, when we have the equation, okay, when we have the equation, we must isolate, or if you don't want to say, we must solve for y, okay, to confirm that y is a function of x. Okay, so for example, is, okay, 2x plus 3y equals 12 a function? And what we do here, we must solve for y. Okay, well, I shouldn't say a function, I have to say a function of x. Okay, if it's a function of x, we must solve for y. So if we have 2x plus 3y equals 12, if we minus 2x on both sides, yeah, we will have 3y is equal to minus 2x plus 12. And then if we divide every single term by 3, yeah, we'll see that we have y is equal to minus 2/3 x plus 4. And you will notice that here, okay, this, for every input, so for every input, we will get only one output. Therefore, this is a function of x. For every input, and I want to say x value, okay? For every input x, we will only get one output y. Okay? Let's look at another example. Is 2x plus y squared equals 9 a function of x? Now, very important, right? When we say function of x, you have to try to solve for y. You have to leave y by itself. So to verify if this is a function of x, we must solve for y. Okay. So we have 2x plus y squared equals 9. I'm going to minus 2x on both sides. If I do this, I have y squared is equal to 9 minus 2x. If I have y squared is equal to 9 minus 2x and I want to solve for y, we will now take the square root of both sides. Okay? We will take the square root of both sides, but be careful when you have square roots, you get a plus or minus. So now we have y is equal to plus or minus the square root of 9 minus 2x. So here we'll have two answers for any x value. For any x value, we plug in. Okay. Example, if x is equal to 0, you'll get y is equal to plus or minus the square root of 9 minus 2 times 0. Y is equal to plus or minus the square root of 9. So y is equal to plus or minus 3, which means that y is equal to 3 and y is equal to minus 3. So you end up getting two values. So what does this tells us? Okay, this tells that the function we have 2x plus y squared equals 9, okay, equals 9 is not a function of x. So this is not a function of x. So anytime you have an equation, you will look to solve the function. And you have to look at what are you trying to solve for. If it's asking for a function of x, what do you solve for, right? Versus a function of y. These are the things we have to look at. Now, how do we check when we have a table? What do we do when we have a table of values? So you'll notice that when we have a table of values, what we do is look for, if it's a function of x, we look for repeated x values. Okay, we look for repeated x values. So let's look at that. So to check if a table represents a function of x, we must look at the table of values and confirm that no x value repeats. Okay? So if we look at two tables here, okay, so x and y. Let's say we have minus 3, minus 2, minus 1, 0, 1, 2, and so on. And if I tell you here the value is 9, okay, here the value is 4, here it's 1, here it's 0, here it's 1, here it's 4. So notice that we have, if you look here, we have no repeated x values. Okay, so this is a function of x. Okay. On the other hand, or maybe I can do it right here. On the other hand, if I have this table, I have this table here, I'm drawing a straight line. And if this is x and this y, and for example, if I have -1 goes to 4, let's do -4 goes to 4, -3 goes to 2, -1 goes to 0, 0 goes to 1. Okay. Let's just make sure. Yeah. And then 2 goes to 6. And if I say -3 goes to 4 again. Okay. So notice here, repeats. Okay. This repeats. So in this table, we have a repeated x value. So this is not a function of x. So you want to be really careful, right? We want to be careful because we are only looking function of x, right? So you want to make sure you stress that it's not a function of x. Okay. So now let's look at when a function increases and when a function decreases. Okay. We want to look at increasing and decreasing of functions. So increasing and decreasing functions. So we can tell if a function is increasing and decreasing by looking at the graph. Okay. We can tell if a function is increasing and decreasing by looking at the graph. So we will use the graph to see when we have increasing, decreasing, or constant. Okay. For example, if we have the graph on the XY axis, okay, that looks like this. So this is y equal mx plus b. Here's the x-axis, y-axis. So you will notice that this graph is increasing. Okay, this is increasing. Okay, and why do we say that? Because if we travel on the graph from left to right, we are moving upward. Okay, we're moving up. Anytime we travel from left to right, okay. So if we look at this graph here now, if we look at this example, okay, we want to make sure we travel from left to right. If we look at this example, here we will be decreasing. So we'll be decreasing. You will notice that anytime the slope m here is positive, Anytime m is positive, we will have increasing. M here is negative. Anytime m is negative, we will have decreasing. Okay. So by looking at the slope at any given point, okay, we can tell where that portion of the graph is increasing or decreasing. So we can, okay, we can tell if a graph is increasing, decreasing, or constant by looking at the slope of the graph at any given x value. Yeah. What do we mean by this? Well, if we look at this picture here, and we look at this little piece here, yeah, notice m is, let's write that, the slope m is negative. Okay? So this is decreasing. Okay? On the other hand, if we look at the slope, let's say here, that piece here, the slope m is positive. This is increasing. So that's how we basically tell if it's increasing and decreasing. Okay. So on a graph can be made up of increasing, decreasing, or many different parts. Okay, many different parts. We can have a graph that has constants. So you can tell on the interval, okay, we can tell the interval for which the graph is increasing, decreasing, or constant. Okay? We can always tell. We can tell where the graph is increasing, where it's decreasing, or where it's constant, always. Okay. So let's look at an example of this. If we have this graph, and let's say the graph looks like this. So here, comes back here, goes over here, and then goes up there. So this is your graph. So let's just put in some values. This is -5. And let's see, somewhere here is 6. Okay. So notice that this here is increasing. This is constant. Here it's also increasing. But here, in this portion here, it's decreasing. Okay. So we have from minus infinity to -5, and okay, from 6 to infinity, we have increasing. Okay, it's two pieces. It's increasing here, and it's increasing here. So that's how come we have this and this. Okay, and then we also have from -5 till, I need to give you a value here. Let's say here is -4. To -4, we have decreasing. Yeah. So if we look at a little picture, that's this portion here. Okay, decreasing. And then for constant, from -4 to 6, it is a constant. Okay? And that's this little piece here. Okay, constant just means we have a horizontal line. Okay, so when we speak for a constant, it is a horizontal line. That's what we're looking at. Some sort of horizontal line. So you should be able to look at any graph and tell where it's increasing and where it's decreasing. For example, determine the open interval on which function is increasing, decreasing, yeah, or constant. Okay. And let's say we have this picture. Okay. If I have this picture here, okay, and if I put in some points here, let's say here is -2, let's say here is +1, and let's just say here is 2, doesn't matter. And this is the function g of x, okay? This is the function g of x. So notice that this portion of the graph, okay, this portion here is increasing. And not only that, this portion here is also increasing, right? So we have increasing here, and we have increasing here. And if you notice that this portion of the graph here is decreasing. Okay. So we can say that this function is increasing on the intervals, okay, two intervals from -infinity up to -2, and then we have from 2 to infinity. And to bring them together, we use union. Okay, we use the union. And we can say that it's decreasing on the interval, okay, from -2 to 1. From -2 to 1. Okay. Now we did say open intervals, right? So whenever we're writing increasing and decreasing, we generally don't pay attention to the close parentheses. We just usually write them on some open interval. Okay. So increasing and decreasing, we're really just looking for the slope, or you can look where the one x value is lower, one y value is lower than the other. Okay. Let's now look at a quick review of zeros of a function. Okay. So zeros of a function. Okay. And remember, another word for zeros, okay, other word for zeros, okay, we will look at the answer. We will look at the solution. We can think of this as the x-intercept. So when someone asks you to find the zeros, they're really just asking you to find the answer. So example, if I say find the zeros of 2x plus 5 equals 8. Okay. So to do this, we'll take 2x plus 5 equals 8. And if I solve for x, so we'll minus 5 on both sides. We have 2x now is equal to 3. And then we divide both sides by 2. If we divide both sides by 2, we have x is equal to 3/2. So this here is your answer, or your solution, or the zero. And the reason we call it zero, is because if you look on the number line, or even the x-axis, x equals 3/2 will be somewhere over here. Okay. But notice that the y value is 0. Okay. The y value is 0. And that's why we call this the zeros of the function. Okay. You will notice for quadratic, right? If we have another example. Okay. Find the zeros f of x is equal to x squared plus 7x plus 12. Okay. So since we know that y is equal to 0, okay, or we also know to solve quadratic, f of x must be equal to 0, or y must be equal to 0. Okay, so if we have x squared plus 7x plus 12 equals 0, here we factor by factoring. We have x plus 3 times x plus 4 is equal to 0. Therefore, x plus 3 is equal to 0, or x plus 4 is equal to 0. So here we have x is equal to minus 3, or x is equal to minus 4. And these are your zeros. Those are your zeros of the function. So zeros is just solving for a function, okay? Now, the next thing we want to look at, or the last thing I'll say, is even and odd function. Even and odd functions. Now, so this is sort of like very similar when we did, we had checked for symmetry, really. So a function is even when f of minus x is equal to f of x. Okay? So what do we mean by this? Example, if I tell you that f of x is equal to 2x squared plus 1, okay, find f of minus x. Well, f of minus x equal to 2, but in parentheses, we put now minus x squared plus 1. And if we square a negative, okay, we will see that this now becomes 2x squared plus 1. So notice that f of minus x, this here is f of x. Okay. So this is an even function, right? This is an even function. Okay. Now, not all functions are even functions. Let's look at this example here. Is g of x equals 3x squared minus 2x plus 5 an even function? And remember, to check for even, right? To check for even and odd, all we're doing is replacing these things. Yeah, we're replacing them. Okay, so we want to know, we want to check if g of x is equal to g of minus x, or g of minus x is equal to g of x. So let's find g of minus x. So g of minus x is equal to, remember g of x is given, right? G of x is equal to 3x squared minus 2x plus 5. Okay? So g of minus x will be 3, and then in parentheses, minus x squared minus 2, and then in parentheses again, every time we see x, we plug in a minus x. Okay? So g of minus x will be 3x squared, because if you square a negative, you get x minus x times minus x. You get a positive x. And you have plus 2x, because when you distribute here, plus 5. And notice that this, okay, this is not g of x. Okay, this is not g of x. Notice here, there is a plus sign, and there's a plus sign here. So the signs here, that was minus. So g of minus x does not equal to g of x. This is not an even function. This is not an even function. Okay. So those are the things you will see. Okay. those are some of the things you will see. Now for an odd function, okay, for odd functions, So for odd functions, f of x is odd if f of minus x is equal to negative of the function you have. Okay. So that's what we have to look for. Now, let's look at examples. Example, f of x is equal to x cubed minus x. So find f of minus x. So f of minus x will be, wherever we see x now, we put a minus x cubed minus, and once again we have x, so we put minus x. Yeah. So by doing this, we end up with f of minus x is equal to minus x cubed plus x. Because if we cube this, we'll get a negative result. Okay. And notice that this here, if we factor, okay, if we factor minus 1, we get minus 1 times x cubed minus x. And this is f of x. So here we have minus f of x. So f of minus x is equal to this. So this is odd. This is odd. Okay, that's odd. So to check for even and odd, yeah, we just have to make sure that we just replace those values. Okay. Let's look at one more example. Yeah. Is the function g of x equals the square root of 2x plus 11 odd. Yeah. And we want to remember, okay, that for something to be odd, g of x must be equal to minus g of x. So we want to check this. So let's figure out g of x is given as the square root of 2x plus 11. So g of, let's do that in black so you see what's happening. G of minus x, yeah, that is equal to the square root of 2, and we have minus x plus 11. Yeah. And if we simplify this, g of minus x now, minus x is equal to the square root of minus 2x plus 11. And notice that this is not the same as that. Yeah, it is not. So this here, this is not g of x. So g of minus x does not equal to g of x. So this function is not odd. Yeah, we're looking for odd, yes. So you will need to practice and do as many examples as always to see where you stand with this. As I always say, try as many examples as possible.